Assalamualaikum and a very good day. We are from Group 7, Chemical
condenser will condense the vapor into saturated liquid. So the phase in the inlet of the pump will be saturated liquid too. So we assume the inlet temperatures of the pump to be 175 degrees and the pressure 0.9 megapascal, which will result in a saturated liquid phase. Besides, we have set a very high value for the mass flow rate so that we can have more power output from the turbine. The efficiency of the pump is 52.92% as there are energy loss caused by the frictions and the leakage. The pump will pressurize the saturated water out to a high pressure of 30 megapascal as we wish to increase the boiler pressure as well as increasing the efficiency of Rankine cycle. The compressed water is then transmitted to the boiler. The boiler will receive the water in compressed liquid from the pump. We assume the water is heated out to a very high temperature of 600 degrees Celsius, as superheating the steam to a high temperature will help to increase the efficiency of the cycle. This is because superheating to a higher temperature will decrease the moisture content of the steam at the turbine exit. The turbine will receive the superheated steam from the boiler, and it will extract the thermal energy from the superheated steam, and the energy will be used to do work on a rotating output shaft. During the process, the velocity, temperature, and the pressure of the gas are sacrificed to rotate the turbine to generate the shaft power. Thus, the pressure and temperature will drop, and we assume it is dropped from 30 megapascal to 0.9 megapascal, and the temperature from 600 to 175 degrees Celsius. The phase of the superheated steam is now changed to the saturated liquid vapor mixture. And last, for the condenser will receive the two-phase liquid vapor mixtures and cool them to the liquid state by transferring the heat to the cooling water system. The phase change takes place in the condenser, and thus there is no change in the temperature and pressure. The pressure remains as 0.9 megapascal, and the temperature remain as 175 degrees Celsius. The saturated liquid will leave from the condenser and then transmitted back to the pump. We have used the icon to build a simple Rankine cycle for a steam power plant. And here is the process flow diagram of the steam power plant by using the icon simulations.
This is the proposed solution and calculation. After we perform the energy balance of all components to find the Q in, Q out, work in and work out, we got to see that there is a slight difference between the result we got from the icon and the one that we calculated manually. So how to explain this? This is because icon, as a simulator, they take more condition and parameter into consideration. For example, there are heat losses through the stream, the turbine not acting diabatically, and etc. But then, in the manual calculation, we assume so many things. For example, we assume that there is no heat loss due to the stream, there is no heat loss at the turbine as the turbine is acting diabatically, and etc. So this explains why there is a slight difference between the result we got from the icon data and the one that we calculate manually. So on to the first proposed solution. The efficiency of this steam power plant can be calculated by using the formula of N is equals to 1 minus QL over QH. By using this formula, we got the value of the efficiency of this steam power plant is equals to 0.31. Next, moving on to the actual power produced. By using the formula of work net out is equals to Q in minus Q out, or also can be calculated using the work out minus work in, we got to see that the actual power produced is equals to 46 megawatt by using both value from the icon and the one that we calculated manually. Moving on to the coal required to produce 46 megawatt. Since we are using the low sulfur content coal and it provides 30,080 kilojoule per kilogram of heat during combustion, by using the formula of QL over Q, QL is the one that we got from the data and Q is this value over here, we got to see that the mass of coal required if we're using the icon data is 4.95 kilogram, and the mass of coal required if we are using the data from manual calculation is equals to 4.88 kilogram. On to the next one. We know that one cycle of this steam power plant will produce 46 megawatt of power, but then our goal is to reach a total power of 1380 megawatt of electricity. So in order for us to reach this amount of value, we need.
Now we will continue the presentation with the conclusion and the recommendation part. Overall, we can say that the high-tech steam turbine Mitsubishi TRX12 is capable to produce required value of power, which is 1380 megawatt. However, the net work done by the equipment such as pump, turbines, generators, condensers and boilers must be in 30 cycles. This is because they can only produce 48 megawatt of power in a cycle. To make this happen, we need 4.9 kg of low sulfur grade coal as a source of power. Experimental results shows that the thermal efficiency of a system plays a crucial role in producing the product. Hence, increasing the temperature of heat supplied into the boiler will reduce the amount of fuel needed to heat the feed water inside the boiler. So, hot steam will be produced with a smaller amount of fuel. Further research is recommended to determine the maximum achievable efficiency. That is all we have for today. Thank you for listening.